give us some insights into the discoveries that led to the Nobel Prize. Hans, please.
I will start by explaining to you a concept from the citation that might not be familiar to you, and that's the concept of topology. So I brought my lunch, and here you see, it's a cinnamon bun. Here I have another thing. I have a bagel, okay? And here I have a pretzel. It's a Swedish pretzel with 2 holes in it. Now, for us, you know, these things are very different. This is sweet, this is perhaps salty, different shapes, etc. But if you are a topologist, it's only one thing that is really interesting with these things in which they differ. This thing has no hole. The bagel has 1 hole. The pretzel has 2 holes. The number of holes is what the topologist would call a topological invariant. And just as you cannot have a half a hole or 2 2/3 holes, you can, for a topological invariant, only have integer numbers, okay? Only integers. And another thing which is very important for the following with topological invariance is that it takes something to change the topological number. I take this thing, you see, I can bend it a little bit, compress it, but in order to make it to change number of holes, I have to do something drastic. I have to break it apart. And this stability of the topological invariance is going to be important. The real breakthrough came with the discovery of one of today's laureates, David Thouless, who could show that these steps here actually can be explained as such a topological invariant. It's not exactly as the number of holes in a bagel or a pretzel, but it's something very, very similar. And this also explains why it is so precise, why it's so robust, why you get integer steps. And later on, 1988, Duncan Haldane, another of today's laureates, showed that you could do the same without having this very strong magnetic field. And for the continuation of this field, that was very, very important.